Gonna check if it's recording. It is recording. It is recording. Cool. Phenomenal. Great. I am going to spend some time talking about what are Bloom filters, why they exist, how they help us solve a problem called set membership, what that essentially means, and what it means to have a very practical implementation of Bloom filters themselves. So, firstly, the why behind Bloom filters. Why do we even need a thing called Bloom filters, and what is the problem statement that arrives us to a solution like Bloom filters? So, let's consider we have an app like Instagram or TikTok, essentially any one of those with scrollable content. So, reels and things within those realms. And one of the really cool things about reels TikToks is that they're served to us from a recommendation engine. What does that mean? It means that any arbitrary user like myself or anybody else requests for reels that are recommended specifically for me, and the recommendation engine does its own set of yada 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 and ends up sending back reels. Essentially, the recommendation to us engine to us is essentially this very big black box, and we end up seeing a bunch of reels that are very tailored to us, recommended to us, so on and so forth. But one of the interesting problems is is that when writing software, one of the things that I've learned about, which applies generally to writing software, is something called the single responsibility principle, which means that if the recommendation engine has its sole purpose to actually recommend reels to users and to figure out what are reels that should be recommended to this user X who has asked for their recommended reels, the recommendation engine should solely focus on figuring out what those recommended reels are and nothing else. Essentially, as the name suggests, single responsibility principle. But there's a interesting problem here. The problem is that since the recommendation engine is solely focusing on figuring out what are reels that should be recommended for a user, there is actually no real check going on for if the reel that has been recommended to the user has already been seen before by the user themselves. What does this mean? So let's say the first time I go to an app like TikTok or Instagram, I actually see a bunch of these reel IDs. What are these reel IDs? These reel IDs are essentially just a representation of the reels themselves. So the unique IDs for reels that may be stored in Instagram or TikTok's database. So we have a helicopter flying reel, we have a baby reel, we have baby two reel, blah blah blah. And let's say the second time, so essentially iteration two, the second time I actually open Instagram or TikTok, I see a baby X ID, a baby X2 ID. These are two different reels. But I also see again the helicopter flying reel ID. When I say see, I mean the recommendation engine has actually recommended these three reels the second time. If we look closely, this reel is actually the same as this reel, which means that it has been recommended before. So the question is that if the recommendation engine, it has actually no part to play in figuring out if this reel is a duplicate of what I've already sent before, how do we store the ones I've already watched? Is the real question. How does the recommendation engine figure out what are reels that have already been watched by the user who is requesting for these reels? And the reason we want to focus on that is so that a user isn't looking at the same reels continuously, since it would lead to bad user experience, so on and so forth. So on the question, how do we figure out duplicate reels that have already been seen? There are a couple of options for storage, essentially, to solve the problem that we've just talked about. So before we think about like these high level sort of structures like databases or like a key value store and like store it somewhere in cache, essentially, just draw one of those system design boxes, what we can do is think even more fundamentally. Let's think data structures, the very fundamental data structures. So if we were to think arrays, for example, let's say I am a user, I requested for let's say, these set of reels that actually got recommended to me, and all of these reels are stored, let's say, in an array. The IDs of all of these reels is actually stored in an array. Let's say the second time I actually request for reels, I get these set of reels. Now, to make sure that none of these reels are actually the ones that have been recommended to me before already, what we're going to do is we're going to iterate through this entire box, this entire array, and we're going to then check that if anything here exists here, essentially this becomes an O of m times n check, where this is where m is the length of what we got here, n is the length of what we got here, and this is highly unoptimal for the very reason which is obvious, which is we don't want anything to have an extremely unoptimal latency. And if it isn't obvious, there's actually an even bigger problem here. For very commonly, for very frequently using users who use the app very frequently, essentially, so the Instagram and the TikToks of the world, they would have, God knows, millions of reels recommended to them constantly. So for every single time that people open Instagram, we have an O of m times n check, which is extremely unoptimal. Add that onto the fact that it's extremely unoptimal on space too, because what we're essentially saying here is that we're storing all the reel IDs across the life cycle of the app, of the user. And let's consider another case. Let's say one of these reels actually gets deleted. The person who actually posted this reel actually gets deleted. Well, now we have this unused space which is storing the ID here, which is of an ID that actually doesn't even exist anymore, and potentially might point to a new reel, because that reel got deleted and potentially a new reel could hold this helicopter flying reel ID, which is extremely unoptimal. And therefore, using just plain arrays is not the solution here. And that's one because it's extremely unoptimal on time, because we're constantly going to be doing an O of m times n check, and we're going to be doing that for every time the user opens the app. And secondly, for space, which is arguably the bigger reason here, because we're going to be storing millions and millions of reels in memory in an array, and even if it's stored on disk, while we're still storing millions and millions of reels, just so that we can have reels be recommended appropriately, which is very unoptimal. Well, in theory, there can be a slightly optimized approach, obviously, with binary search, given that all of these IDs are somehow sorted, and through through a binary search approach, we can reduce that search to be log n. However, again, we're still going to be doing m times log n, which is still extremely unoptimal for the scale that we're actually dealing with, and for the number of reels that actually get recommended per user, and how frequently it gets recommended per user. And again, as the third point here suggests, space complexity is something we've already talked about, which is that throughout the life cycle of the app, there'd be millions and millions and millions of reels, and it really makes no sense to have something as unoptimal as using arrays, or even optimizing time complexity slightly with binary search, because it's doing nothing for this space. The next thing that we get onto is the intuition behind Bloom filters. What does that even mean? So right now we looked at arrays as our possible solution. Sure, we can look at trees too. Let's say, we can look at self-balancing trees. We can go as fancy as we want, but the underlying problem here, or the very big problem here, is that even space, right? Even if we were to use trees, and even if we were to have one of those logarithmic searches, well, space is still really unoptimal, because we'd be storing all of those real IDs. And a Bloom filter is essentially created to solve a problem exactly like this, where space is an extremely big bottleneck for a solution that we're trying to create for a problem like this, where we need to find duplicates, and we need to do it with extremely low latency, um, and it just doesn't make sense to store that much per user. And again, even if we were to use something like, or even if we were to abstract everything out and say, well, we can store everything in cache, even then we're going to be storing such a large amount of data per user, basically all the reels that they've watched through the life cycle of the app, and we cannot even attach possibly a time to live against the cache itself, because For example, if the time to live attached is, let's say, 30 days, well, on the 31st day, they could, in theory, be recommended a reel that it's seen on the second day, for instance. And ideally, we'd like to avoid any of those scenarios, and ideally, we'd like new reels based on the most updated preferences of the user itself. So, any approach to do with storing all reels to make sure we can check for duplicates is out of the window, unoptimal on space, unoptimal on time. And this is where the intuition behind Bloom filters comes in. So as we see here, our worst case time complexity, well, in theory, our best case from what we just saw from our previous examples is m log n, where m stands for all the reels that have just been recommended, and n in the log n stands for checking against all the reels that have previously been recommended. And this n, as we've talked about, can be really, really big. So we need to optimize in a way that reduces this complexity by a big margin. Ideally O of 1, but that how we're going to get there is something we're going to see, and it isn't directly intuitive. It wasn't to me either. And also the space complexity issue. We need to get away from storing all reels throughout the lifecycle of the app, because it makes no sense again. So how do we do it? And one of the things that I learned about, and I don't even know if this is an actual theory, but I just heard someone talk about it, is the theory of opposites, which means that if something were to hold true based on a certain condition, how about I just eliminate that condition? What does that mean? So currently we're storing the reel IDs of all throughout the lifecycle of the app for all the reels that the user has watched. What if I just don't do that anymore? What does that mean? So what if I don't store the data itself? Which means that I need to, without storing the IDs of the reels, figure out if that reel has even been watched when I have no record of that, if that reel has even been watched. Does that make sense? So hence, when we say to just not store the data itself, what we're considering is that throughout the life cycle of the app, the reels IDs that we were storing, we would just not store any of them anymore. Which means that we need to now figure out a new solution. And this is where the concept of Bloom filters and what they do actually comes in. But before I even talk about Bloom filters and how they actually solve this problem, more than how they solve this problem, let's first talk a little bit about Bloom filters and one of the things that they actually use, which is hash functions. What are hash functions? Hash functions are essentially this black box that we can think of, where if you give it a certain input, it gives out a certain output. And every time you give it the same input, it gives out this very same output. And in theory, it's also possible that for two different inputs, it can actually give the same output. However, one of the things about hash functions is that for the same input, it's always going to give the same output. Let's take an example. If I were going on a water slide and I was to go into one of those water slides which eventually has you land in the river, or like this pool type thing. Every time I go in the slide, I am always going to land in the river. Let's say if I have one of my friends who goes through that water slides, who lands in the river on his head, and I actually land on my back. Every time I go through the water slide, I am always going to land on my back. Every time my friend goes through that water slide, he is going to land on his head. And this water slide here, which is the middleman or the middleware, or whatever you'd like to call it, is what actually represents the hash function, which means that for every time you put the same input, which is Anish going through the water slide, it's always going to give the same output, which is Anish landing on his back. And every time you, let's say, put another output which is intended to land on its head, let's say if one of my friends is always going to land on his head, every time he is going to go through the water slide, he is going to land on his head, guaranteed. That's a property of hash functions itself. However, there is a possibility where if, let's say, one of my third friends goes through the water slide, he could also land on his back. What that means is that a hash function can produce the same output for two different inputs, but those that output is going to always be the same for those two inputs and for any other input that produces that output. And if this is not clear, I would how I understood hash functions was just through GPTing, and that's probably I would do again if I don't understand hash functions. But the idea here is that it is this black box where you can put in inputs, you can get an output. The output is always going to remain the same for a specific input that you put in. So if you put in Anish, you're always going to get abracadabra. If you put in, let's say, Aryan, you're always going to get dabra ka abra. And if you put in Anish again, you're going to get abracadabra. It's always the truth, and that's how hash functions work. So now, here, how are hash functions useful in Bloom filters? All right, we talked about hash functions. Now let's get back to Bloom filters. What Bloom filters actually do is that instead of storing the data we talked about earlier, which is, all the IDs of what the user has actually watched, we instead store bits. We essentially 0 and 1 values, and we don't store the number of bits that we actually store is actually not equal to the number of real IDs. It is just this certain fixed size, and what this size would be, how do you determine the size, or things to talk about later, but just this fixed size array which has a bunch of these zeros and ones. Now, conceptually, to understand here, as we talked about earlier, hash functions would take in a certain input, would give back a certain output, and that output could, let's say, be some arbitrary integer value. And that integer value could be determined by how big the hash space is. It could be anything within that hash space can allow. And when we say hash space, just think of this extremely big range of numbers. And in this big range of numbers, you can have a certain integer value that would be returned. So let's say we had this real ID 1. For example, if real 1 was actually the ID of a certain reel that is recommended to the user, we pass it through the hash function, and whatever format this is in, let's say this is a string or whatever it is, somehow we pass it through the hash function and we actually get back a certain value. Let's say we get back 253, for instance. The size of the array that we talked about with zeros and ones, this type of array doesn't need to be a size 253. It can be of any size. And to make sure that whatever value we get back is actually in the size of this array, we actually mod it by the size of the bit array itself. So let's say if the size of our bit array in this case is 36, we actually mod it by 6, and that essentially gives us a value between 0 and 6, for instance. Now, once we've gotten a value between 0 and 6, now why we're actually doing this, we'll get to in a second, but follow me for a second because this is how I ended up learning about it. So let's say we had a real ID 1, passes through a hash function, gives us 253, we mod it by 6, get a value between 0 and 6, which means that it can now fall in between one of the indices between the bit array. We then check the index of that value that we got. So we got a value between 0 and 6, let's say we got 4. We checked at index 4, which is this value, if this value is 0 or 1. If this value is 1, it means that this reel has already been recommended and we actually ignore this reel. And if this reel, and we check if the reel, and if what we check is that if the value is 0, this reel has not been recommended, and then we actually send it to the user and we actually recommend it to them. How did we arrive at this mechanism? How do we know this actually works? And what are some of the potential pitfalls is what I would talk about here. But the fundamental understanding of what Bloom filters are doing is that it's taking each of these real IDs, it's passing it through a hash function, it's modding it by the size of the bit array that is stored for every user, it's going to the index, checking if that value is 0 or 1. If it is 1, it's discarding that reel. If it is 0, it means that that reel has not been recommended to the user and is actually sending it to the user. There is nuance here, but I'll come to what that nuance is. But this is on a high level what's happening here. And for each user, we are now storing this specific bit sized bit array. There are two great things that are happening here. One, at this point, the only thing we're iterating to is the reels that have been recommended to the user. We're no more keeping track of all the reels that the user has previously watched. We're just keeping track of the reels that have been recommended by the recommendation engine. We're passing it through a hash function and modding it by the size of the array. That's an O of 1 operation, so there's nothing additional to the time complexity. And we're checking if at that specific index, if the value is 0 or 1, again an O of 1 operation. So we've reduced our time complexity to what in the worst case was O of m times n to suddenly just being O of m. And O of m is always going to be a relatively small number, and it's not going to be anything close to a million. It's always maybe in theory going to be between 0 and 200. For instance, if 200 is the number of reels that the recommendation engine spits out for per user, and this bit array is again just fixed size. It doesn't keep growing constantly, it doesn't go to a million. It's this fixed size array which is relatively small in length. Now, this is on a high level, right? But how do we know this actually works? Does this even work? And what are potential pitfalls are things that essentially need to be talked about here. Resizability and hash collision handling. Hash collisions are a byproduct of using hash functions in a use case like we talked about here. And hash collisions is actually what gives Bloom filters the definition it actually has. Bloom filters, by pure definition, is actually a probabilistic data structure, which means that the example that we saw previously with these zeros and ones, yes, we're currently saying that if there is a 1, it means that the reel has been watched. If there's a 0, the reel has been not watched. There isn't a guarantee that it's going to be true. But there is one guarantee that we can give, which I'll talk about in a second. Bloom filters can actually give out false positives. What does that mean? False positives essentially in this case would refer to, let's say if I had a certain reel ID, I passed it through the hash function, and then I modded it by the size of the bit array itself, and I, let's say, checked in the bit array the specific index. What would happen is that at that specific index, let's say I saw a 1. And as we earlier discussed, a 1 would mean that, right, I watched that reel and therefore we don't recommend it. But a concept behind Bloom filters' probabilistic nature is that it can give out false positives, which means that this 1 doesn't actually guarantee that the reel has been watched. However, there is a guarantee that if the value is at 0, the reel has definitely not been watched, which creates this false positive nature and hence is given the term a probabilistic data structure, which means that if a user asks the recommendation engine, can you please recommend me a bunch of reels? It recommends it with, let's say, reel ID 1, 2, 3, 4, 5. There is a possibility the reel 3 goes through the hash function, size of the bit array, gets modded, and goes to, let's say, the index 2 and sees that there is a 1. There is a possibility that this reel ID 3 has actually not been watched, but the bit array says that it has been seen before. And that is because the bit array actually suggests that there is a 1 at that location. However, that is not true. And that's what creates this probabilistic nature. Why does this happen? Because if you really think about it, how we talked about hash functions previously with an example, right? A hash function is black box, where an input is always going to give the specific output. However, two inputs can also have the same output. What that means is that if reel 1 went through the hash function modeled by the size of the array, and let's say first saw a 0, it would convert that bit to 1 because obviously now the reel 1 has been seen and therefore it shouldn't be recommended again ideally. However, reel 3 on going through the hash function, this box that we have here, could still give out the same output. Why? Because two different inputs can go through a hash function and give the same output. which means that it would go to the same location in the bit array and see, oh, well, there's a 1, therefore it's probably been watched, when it actually hasn't. And that's one of, well, the limitations or the trade-offs you make while using Bloom filters. But this is still fine, and this is actually acceptable, because it's okay if you miss out on certain reels, but what you really want to avoid is duplicate reels. And that actually works out here, because if there is a 0, it means that that bit has actually never been touched, and therefore it means that the reel that would actually end up on this index after the hash function has definitely not been watched. And hence comes in the concept of handling hash collisions or resizability. So Bloom filters can essentially have spikes in error rates, and if you really think about it, it's slightly intuitive as to why that would happen. Because when we go through these reels, and let's say we have a million, as we talked about earlier, we'd have millions and millions of reels that are being recommended to these users. If this bit array is actually really small, the range of indices that can constantly be hit to check for ones and zeros is actually pretty small. And if we have a million reels against just an array of size 6 with bits, well, it's obvious we would constantly be hitting the same indices based on certain reels, and therefore we can have more error rates. And when I say error rates, we mean here essentially the false positives, right? And to avoid that, you can actually resize. The Bloom filter to a slightly larger size. Now, if you think about it, if I'm resizing the Bloom filters, I would actually need to again start over this process of zeros and ones, and that's a trade-off we again choose to make, right? However, that is one of the approaches where you actually resize the Bloom filter itself to actually reduce error rates. And again, as we talked about here, we linearly increase time complexity for resizing, but we accept the trade-off now, because for most operations, which is, let's say, this is a random number, like let's say for 95%, 99% of operations, we're actually just asking the recommendation for the reels. The recommendation engine is just doing this O of M check, where this M is actually, we've assumed a number between 0 and 300 for what's being recommended, and just sending it back to the user. And this is significantly more optimal than what we were doing earlier, which was our possible case with O of M times N or O of M times log N for every time a user asks the recommendation engine for reels. And now what I actually have here is the code for what a possible Bloom filter could be. So if you see here, we're just initializing, we have, this is all written in Golang, and let's say we have the initialization of a Bloom filter here. If you look here, we actually have a new user addition. This user is just getting added to a map here, where we say we have a user ID to filter, user ID to size. This size here actually represents the size of the Bloom filter itself. So if you remember how we initially talked about how Bloom filters, where's it gone? Right. So if we talk about how Bloom filters have a bit array which has a specific size, in theory, if I'm a user who actually looks at reels a lot, I would probably have a bigger sized bit array than, let's say, somebody who doesn't look at reels a lot. And therefore, there is this map here that stores the user ID to the size of the Bloom filter. And this is the user ID to the filter itself, which is essentially a byte array, which would have 8 bits at each location. And each of those bits can be manipulated as zeros and ones and so on. And what we're doing here, we're creating a new filter. We're adding, so every time we get a new user ID, we're just adding it to the map itself, and we're essentially initializing a new byte array with the size, which for now I've just kept to 5 for the sake of simplicity. And when we say check event here, all it's essentially doing is that it's going into the user ID to size map. It's actually going over this function that is called byte array index, which if we look here is essentially using a hashing algorithm called murmur hash. There's also other, you can also use SHA-256, whatever else. There's a billion others, and it is modding by the size, which is the really important operation so that we actually get something within that index range. And then we do the membership check. We're calculating the byte index and the bit offset. The reason we're actually doing this is because in Golang, you have byte arrays, and inside those byte arrays, at each index, you can have 8 bits. So we're actually getting the index that we need to get to, and then we're also getting the offset of the bit itself. Um, and we then check if that bit is actually zero. If so, we return true. Otherwise, we actually end up just returning false, and we change that bit from 0 to 1 essentially. And we have two examples. We have a simple example here, where I've just checked that for user ID 1, if I have an event ID 1, which could be real ID 1, and then I check again if that has already been checked before. And if we run this code, it first returns false. And the reason it returns false is because it actually doesn't exist in the membership check, and therefore it returns false. And it returns true the next time because, well, we've seen it before and we don't want it to be seen again. And that's what the Bloom filter is doing for us. So that is essentially the explanation here. And hence that was essentially the explanation of what a Bloom filter does, and sort of a high level overview of what code can look like and what it actually means to implement a Bloom filter on a simple level. And this is actually really commonly used again in TikTok, Instagram, and platforms like those, but also in databases as well, and also in CDNs. For example, with databases, the application here is to be able to check if something exists within memory, and if that record, for example, if we even need to go to disk to actually have the check of if it exists or not, because databases would store data in disk, and going to disk is an extremely expensive operation in the context of databases. And if we can avoid that, we try and avoid that. And Bloom filters allow one way to actually be able to do it, because it only introduces false positives but no false negatives, which means that if the Bloom filter says that this record with this ID does not exist on disk, it definitely does not exist on disk. And therefore, that's one of the other applications, along with TikTok, Instagram, and some of the stuff that I've talked about previously. So that is that. My laptop has gone on screensaver, and so have I. So I am going to go to find the next thing to talk about. Thank you.